the Laplace of the derivative is s times x sub s minus x sub 0. Now, you're probably wondering why we care about the Laplace of the derivative in circuit. Well, when you have an inductor with the value of L and a voltage here, V, and a current going through it, I, we know V equals what? L di dt. So when you have an inductor, if you change it to Laplace now, the Laplace of that we know we can factor L outside times the Laplace. The Laplace is an integral, so when you have an integral, you can take the constant outside, di dt. And using that equation above there, this should give me L times what? The value of this one, which is S times I sub s, the current, minus what? I sub 0. Which becomes SL times I sub s minus L I sub 0. And that will tell me actually what do I need to do when I have an inductor. When I want to switch that inductor, when I want to go from time domain to Laplace, well, you're going to find the resistor as a constant. The resistor R, when you switch it to Laplace, it will stay the same. The inductor is not going to be the same. The inductor here, again, this is the current I, this is the voltage, and this is the value of L. When you switch that, it should be replaced with an inductor with the value of S times L, because the current is I sub s going through it. So this would be when you multiply V equals I times the impedance, that'll be this times that, which is this value. But now minus, I got to put a minus to plus here. And what's the value of that? L times I sub 0. So I'm going to replace the inductor by that. Now, if I'm lucky, my initial conditions will be 0. And if my initial conditions are 0, this piece is 0, you end up with S times L. Now, what about if you have a capacitor? Let's look at a capacitor. The capacitor, again, this is the current I, this is the voltage V, and this is C. We know from this I equals C dVc dt. So the Laplace of that is we take C outside times the Laplace of dVc dt. And we know the answer to that one. That's from the top equation today. It's this one. So the current here, not the voltage, the current in a capacitor is going to equal C times S times Vs, oh, I'm using Vc here, yep, the voltage as a function of S, minus the voltage at 0 minus. So that'll be C times S times Vs minus C times V sub 0. What does that mean? If I have a capacitor, not an inductor now, a capacitor, this is current. This is I coming to it. This is the voltage. And this is C, that's in time domain. When I go to Laplace now, this is going to be two current sources. Remember, it's current. And current to split, they have to be in parallel. Not in series, in parallel. And the first one, the value of that 1 over SC. And this is the voltage V. Why is it 1 over SC? I'll wait till you finish writing.
What is 1 over SC? Is it the value?
The value of this impedance. And the reason, Ohm's law says what? Current equals what? Voltage divided by the impedance, right? So the current here will be the voltage, which is Vs divided by 1 over SC. And when you divide by 1 over SC, what does that equal to? SC times Vs. And that's what you want it to be, right? So that's why this one's 1 over SC. You also, this is the current coming down. You want to subtract from it. If you're going to subtract from it, that means there's a current source going upward. And what is the value of that? C times V sub 0 minus. So that's why we're interested in the derivative. Now, I'm going to tell you what the Laplace of the integral there. So the other one is the Laplace of the integral. What is the Laplace of the integral from 0 to t f of t dt? And the answer to that is 1 over s f of s. 1 over s. F of s. And usually going from 0 to t. A lot of times we break that to two parts. We go, okay, from this to this and from this to that. So a lot of times this is written as f of s over s plus 1 over s. This is a constant integral here of f of t, the integral of f of t dt at t equals to 0. Which means really the value is 0. That's what that means. What's the value is 0? So again, let's look at the capacitor versus the inductor. Here's the inductor. This is L, this is the voltage V, this is the current I. We know from this V equals L di dt. We know what the Laplace of the derivative. But we also know that I equals what? 1 over L, the integral of V dt, from negative infinity to t. So the Laplace of that what is the Laplace now of 1 over L, the integral from negative infinity to t of V dt? Well, I can take the 1 over L outside times the Laplace. Nope, I wrote that. The bracket in the wrong place.
Is there anything written in the top corner above dt?
No. Above it? No. Yep. I should have put the integral first, then the bracket. I mean the integral, I'm going to go from 0 to t of v dt plus the integral from negative infinity one over L and this actually will be let's do it this way, one step. Don't like the way I'm writing the stuff here this morning. From negative infinity to 0 I broke it down. Instead of negative infinity to t, can't. I go negative infinity to 0 plus from 0 to t. That's really all I did. I was about to separate into two separate integrals and everything. And you're going to end up actually finally with 1 over L. The Laplace of this will be f of s over s. Plus, and this will be, this integral will give us actually the current at 0. 1 over L, if you do 1 over L from negative infinity to 0, I'll just put it there. 1 over L, the integral from negative infinity to 0, v sub t dt, and you're going to be divided by s actually, because when you integrate it's over s. See the 1 over s here? 1 over s, that's where the s. This happens to be the current at 0. A lot of math this morning. Plus the current at 0. And that's really all I care about is that equation, but that's the math behind it. So this is the current through the inductor, which means if you have an inductor, that's a current by the way, if you have an inductor, here we go, has a value of L, has a voltage of V here, the current I in time domain, and you want to switch that to Laplace. Since you're going to be adding them current, they have to be in parallel. The value of this S times L. I show it instead of F here as the voltage, because we're dealing with the voltage here, right? V, that's the voltage at S. Yeah. F is for any function in general here, so that's really the voltage at S. The voltage across the capacitor divided by S, plus, that's a plus, means pointing in the same direction, I sub 0 minus at S. And let's see, why is it actually SL, not 1 over SL? Because it looks like 1 over SL in the bottom here. Ohm's law says what? The current I equals V over what? V over R, or V over Z. So if I make the Z value SL, what's the current going through it? That's the voltage divided by Z, which is what? SL. Is that what this expression is, the first one? Are these two the same? What I wrote here? That's why it's SL. Plus the initial value divided by 0. Notice it's pointing down because you're pointing in the same direction. There's a current coming down, and you have another one, you're adding to it that current. It's not subtraction where the capacitor was subtractions. This is addition. And let's look actually at, so this is I sub L. Let's look at the inductor now instead of the capacitor. I mean the capacitor instead of the inductor. Yep. Capacitor. I just did the inductor backward. This is plus to minus the voltage, and this is I. We know I equals C dV dt, which means we know the voltage across the inductor, capacitor. It's 1 over C, the integral of I dt. So what is Vc as a function of S? It is the Laplace of 1 over C, the integral of I dt, from negative infinity to t. I can take the 1 over C outside, the Laplace, and I can break that from negative infinity. You know what? Let me put the 1 over C inside, leave it, break it down 2 parts. Yep. I'll leave it, 1 over C here. From negative infinity to 0 I dt. Plus 1 over C, the integral from 0 to t, I sub dt. And what you're going to end up with for a capacitor, this one here will give me I over S. I through the capacitor divided by S, and there's a C in the front, SC. This one will be the integral from negative infinity to 0 of I, that's the voltage at 0 minus, but you're also going to be dividing that by S. Why are we dividing by S? Because of that equation we started the whole day with. It's f of S over S plus 1 over S, the initial condition, at t equals 0. It's 1 over S, the value at t equal to 0. So that's the reason why you have over S in this one. And that's the current. I mean, that's the voltage. This is a voltage here. I, not voltage. This is the voltage across the capacitor as a function of S. So here we go. If you have a capacitor, this is the current through it, I. The value is C. You can replace that with, it's a voltage, so you're going to be adding them. So you're going to be adding them, so that has to be a plus to minus. And I know this value has to be I sub 0 minus over S. What about this? There's I sub S going through it, or I sub C, not I sub S. I sub C going through it. I'm going to be using 1 over SC here. And let's see again why it's a 1 over SC. Going back to Ohm's law, V equals I times Z. I want it to be that answer. That's what I want it to be. This piece, I want this piece to give me that. Let's see if what I did there gives me that. V equals I times Z. We know what I is. That's I sub C. And we know what Z is, according to my calculation, if I did it right, is 1 over SC. When you multiply this by that, what do you have? You have I sub C divided by SC. Is that what you want it to be? That's why the capacitor is always 1 over SC. So that's where actually these came from. It wasn't like, oh, let's, sounds like a good idea. It came out from Laplace. In our book, we have a page that summarizes all of them. And that's this page. It says, when you have a resistor in time domain, you want to go frequency domain, that's Laplace, the resistor stays the same. When you have an inductor, V equals L di dt, the voltage, you can replace it with this circuit, or you can replace it with that. If you're looking for the voltage, we use this, current, we use that. When you have a capacitor, if you are looking for the voltage, you replace it with this. For current, you replace it with that one. And that's what I was just finished actually summarizing or doing for you, is those examples. Now, just to show you how we solve a problem now, knowing these things here, let me take a simple problem. And so tell me what the answer to that. This is going back to probably chapter 8 in our book when we did first time RC, RL circuits. Before we get to RLC even. 9 U sub T (3 ohms) and a capacitor here of a value of what? 0.5. And the question, what is the voltage here across the capacitor? Again, this circuit 9U sub T is equivalent to, that's equivalent to a voltage source of 9 volts, has a switch on it like this. The switch closed at T equals to 0. Here's the 3, and there's the 0.5. Remember what 9U sub T means. You have 9 volts for T greater than 0. You have 0 for T less than 0. So the first thing I do is find my initial condition. The voltage across the capacitor is 0 minus. Since there is nothing going through that circuit, what will happen? 0. Which is the same as the voltage across the capacitor is 0 plus. What happens when T goes greater than 0 now? This is what my circuit looks like. 9 volts, 3, and 0.5. Let me change that. Remember the 3 steps. Change to Laplace. Let me change that circuit to Laplace. The Laplace of 9 is 9 over S, right? The resistor stays the same. In time domain in Laplace, the resistor does not change. Now, the capacitor, I have two options to use. Let's look at both my options. Here's my two options. I can either use this circuit or I can use that circuit. But here's the good news. They both ask me for the voltage across the capacitor 0 minus V0. What was my voltage for V0 for that example? 0. So this piece is not here, neither that piece. So if you take both these pieces out, what do you have left? A capacitor with a value of 1 over SC. This is the Y value, which is 1 over Z, by the way. In case you can't see it, that's Y, admittance. Z is the impedance. That's 1 over SC. The reciprocal of that is SC. So I can take the capacitor now and replace it with 1 over SC. And let me find, this is VC now, let me find the voltage across the capacitor as a function of time. A function of S, not time. So my next step in the three-step process, change to Laplace. That's the first step, right? What was the second step? Solve in Laplace. So let's find the voltage across the capacitor in Laplace. I can use voltage division. Is equal to 9 over S times what? The impedance of that, 1 over SC, over the sum of them. All the rules we learned before are still good. Now I can multiply, this is the big fraction here, I'm talking about this one. I can multiply the top and the bottom by SC to get rid of the fractions. So if I multiply by SC, I'm going to have 9 over S times 3SC plus 1. And C is 0.5. S times, what's 0.5 times 3? 1.5? S plus 1. I don't like that way it looks, 1.5 S. I like to have it S plus a number.
Is there a reason you wouldn't want to multiply the S through?
Because I'm looking for simple roots. Because these are distinct roots, and I can use inverse Laplace quickly, right? But I could multiply it for now and factor it later if that makes it easy on you. It doesn't make a difference. So now what I'm going to do, because I want that to be S, not 1.5 S, because I know the Laplace of S plus alpha, or the inverse Laplace. So what I'm going to do here, take that fraction, which is 9 over S times 1.5 S plus 1, and I'm going to divide by 1.5 and divide by 1.5. Divide each one of them. Or multiply by 1 over 1.5. If I do that, 9 divided by 1.5, is that a 6? I think that's a 6. It's getting pathetic. I got to use a calculator for that. That's a 6, yep. Over S. When I divide by 1.5, that becomes S plus 1 over 1.5, which is what? 2/3? It will look like this. Remember the 3 steps from a long time ago when we started talking about Laplace? We said we take our circuit from time domain, we change it to Laplace. That's step number 1. Step number 2, we take that circuit and solve it in Laplace, which we did. I just solved in Laplace. That's the voltage across the capacitor as a function of s. I did solve it. That's the result of step number 2. And step number 3 is what? Change back to time domain. These are the 3 steps. Go from time to Laplace, step number 1. Solve it in Laplace. We did that. Now change it back to time domain, which means I need to find the inverse Laplace of that. And Tom, that was the reason why I left it like this. So now step number 3, what is the inverse Laplace of 6 over s times s plus 2/3? Well, I can write that of a over s, or k1, k2, whatever, and b over s plus 2/3. And to find a, I'm going to a sitting on top of s, so I'm going to take s out of the picture from this expression. It's 6 over s plus 2/3 when what? When s equals, what value makes this one 0, the bottom 0? 0. So that's 6 over 2/3. I think that's a 9. And to find b is sitting on top of s plus 2/3. So I'm going to take s plus 2/3 out, 6 over s, when s equals what? Negative 2/3. And that's a negative 9. So then the question becomes, a is 9, so 9 times the inverse Laplace of 1 over s minus 9 times the inverse Laplace of 1 over s plus 2/3. And the answer to that, that's 9 times, what's the Laplace, inverse Laplace of 1 over s is 1, minus 9 times, what's the inverse Laplace of that? That's e to the minus 2/3 t. So if you want to factor a 9 out, 9 times 1 minus e to the minus 2/3 t. U sub t, because remember your circuit does not have anything till t equals to 0. And that's how we're going to solve all these problems.